And this paper, the topic is semantic segmentation. It uses the generative models and the semi-supervised learning to realize the strong out-of-domain generalization. And I will introduce this paper from the following contents. First, I will give you some background information about semi-supervised learning and semantic segmentation and out-of-domain generalization. And then I will introduce this proposed method from the overview, training, and inference phase. Next, I will show you some experiment results. Finally, we will land on the conclusion. Let's come to the first part, the introduction. Let me give you some introduction about the semi-supervised learning and semantic segmentation. We know that if we want to train a model for semantic segmentation, we need a large amount of labeling data to realize the supervised training. So the labeling.
Jessica,
yes.
We're still with the title page. Somehow your PPT is not moving. We're still with the title page on the display.
Now can you see my PPT?
No. So we're just seeing, we can see the title page right now. I think you're on page 3, slide 3, right?
Oh, yeah.
We're with slide 1.
Oh, please wait a moment. There's something wrong with my computer, I think. So now can you see the third slide, the 4?
Yes. Now we can see. Yes.
Ah, okay. So let's begin at the introduction. First, I will give you some information about the semi-supervised learning and the semantic segmentation. We already know that for the semantic segment task, we need large amounts of labeling dataset for supervised training. So labeling large dataset for this task is very time consuming. Recently, some papers have proposed the semi-supervised learning so that to make the learning with small labeled dataset by augmenting the training set with large amounts of unlabeled data. And the most widely used semi-supervised learning strategies include the following 3 strategies. The first one is the pseudo labeling, and the second is consistency regularization, and the last is the data augmentation techniques. Even though the semi-supervised learning strategy has achieved the performance improvement for the semantic segmentation, however, it's still easily overfit to the training dataset. And so in this paper, the author want to solve this problem and realize the out-of-domain generalization. So you may be curious about what is out-of-domain generalization. Here is an example. We want to train.
Before you go on, can you describe a little bit of a pseudo labeling, consistency regularization? Those 2 that you mentioned on semi-supervised learning.
Okay, I will briefly introduce about these 2 strategies. For the pseudo labeling, we know that in the semi-supervised learning, we have some labeled data, and we can train the model first just use the labeled data, and then we can input the unlabeled data to the trained model, and we can get some pseudo label for the unlabeled dataset. Then we use the generated labels for the unlabeled data to do the training in a supervised manner. And through this training alteration, we can improve the performance of the model. This is about the pseudo labeling. And consistency regularization. It is similar with about the teacher-student strategy. We can enforce some constraint on the model by using the consistency regularization of the output of the labeled data and unlabeled data, so that realize the improvement of the model. Actually, these two strategies is also long stories, so we not focus on these two strategies in this paper, so I don't introduce more about these two.
Thank you.
Thank you. Let's continue. Here is two examples for the out-of-domain generalization. And the first one, we can see that we train a model with the face image and its label. And we test it on the out-of-domain test images. For example, the paintings, the sculptures, and the cartoons, and even for the animal faces. We want to realize the high performance on these out-of-domain test images and get the segmentation result of these test images. And we can see in the below, here, the training data is the X-ray and CT data. And we test on the other data sets which collected from the other sensors, or maybe this test image has the different patient poses with the training set. And we want to realize the segmentation on this out-of-domain test images. So here is the brief introduction about the out-of-domain generalization. Let's come to the main content, the proposed method. Before introducing the proposed method, let's see this figure. The author want to achieve the semantic segmentation by using the GAN model. And this figure is an example of the steel GAN. It is also the baseline of this proposed method. We can see that from the steel GAN V2, we input an image, and through the encoder and generator, we can reconstruct the image. And through the adversarial training and image reconstruction laws, we can realize the reconstruction of the input. And here, the author posed a question that if a model can generate realistic image, so this model should also know how to generate the corresponding pixel-wise labels as well, because we have already know that reconstruct the image from the input is a very tough task. However, the pixel-wise labeled for the reconstruction, it just needs the high-level semantic information. So the motivation comes from this idea. And the author proposed his method. He used the baseline of the steel GAN V2 and the novelty lesson. He tried to augment the baseline with a label synthesis branch and learn the joint image label distribution, so that he can realize the semantic segmentation of the reconstruction. And he also used the semi-supervised training scheme. Through the semi-supervised manner, we can make the use of large amounts of unlabeled data. So the data set is a large set of unlabeled images supplemented with only few labeled ones. And let's come to the training process. We can see that there are two inputs for the proposed method. The X represents the input image, and Z represent the noise vector. And we first put the X to the encoder, and the encoder is designed by the DeepLab V2. And through the encoder, we can extract the features. And the latent noise vector, we will send them to a fully connected network so that we can make it in a complex space. And the generator takes the features and the latent code to reconstruct the image, the input image, and the corresponding labels. And the training process include two parts. The first part is the optimization of the generator and discriminator. They are trained with the following standard GAN objects. We can see that the first and the two function are the object of the discriminator, and we want to maximize these two functions to realize the optimize of discriminator. And the third is the loss function for the generator. We try to minimize this function to realize the update of the generator. And the generator
hang on a second. There,
yeah.
You have two discriminators, right? D sub M and D sub R. What are they?
Okay, I will explain. The discriminator DR is try to discriminate between the real and fake image. It is similar with the standard GAN. And for the DM, it is used to discriminate between the real and fake image label pair. We can see that after reconstruct the image and the corresponding label, we do the concatenation of the image and label. And the DM, the input, is the image label pair.
So you're talking about the pair of the
image and the
RGB
label.
image and the segmented image. Is that what you're saying?
Yeah, exactly.
And so the discriminator looks and say, okay, if you segment this image, it would come out like this. And that's what it checks for.
Yeah.
Okay. And so, but then in this structure here, I'm still kind of confused because on that figure, image X and the reconstruction doesn't match, right? At least out of the generator. So what is that? That other woman's image?
This is just an example. It may be a middle process, the reconstruction. Actually, I think we should try to this part should be similar with the input. Here is just an example, an instance. We try to.
So the generator outputs two image maps. Then one reconstructed image and then segmented image.
Yeah.
So it has two outputs. Okay.
Yeah, exactly.
And when you so DR basically is just like any other GAN, right?
Yeah, exactly.
All right, that's a discriminator for any other GAN.
Yeah.
And for that matter, E and G are like a conditional GAN here, right? Or am I not reading it right? Well, style GAN, basically. So you have an input and you put the input as the condition image. So it's a conditional GAN, right?
Yeah, exactly.
right? And so you transfer the style,
Yeah,
and that's what it is then. Okay, all
Yeah.
right. So it doesn't match the input image. It looks different, but style is what you transferred here.
yeah, exactly.
In that case, then this image reconstruction loss you compute, it shouldn't be low here, right? Because you're transferring the style. So it's not going to match input image. You transfer the style.
Yeah, you're right.
Okay, and so the whole idea is that you use this and using the supervised loss for the label image first,
Yeah.
and then how do you compute the supervised loss with unlabeled images then? You mentioned about semi-supervised method, so you're going to be using the unlabeled images here in the second phase of the training, right? And so that doesn't come into play, I guess, in the second phase of the semi-supervised learning.
Actually, the supervised loss is this part. It is just used to calculate on the labeled image.
Okay.
Yeah. And
okay. All right. And so for you're utilizing, I guess, labels generated from your semantic or segmented map that you develop from the unlabeled image, and then feed it back as a supervised labels.
Yeah.
Okay. All right. I just want to get a rough idea what the overall training is.
Yeah.
Thank you.
Thank you. And the design.
I also have some question, Jessica.
Yeah.
At the top, so you have the segmented image path, right?
Yeah.
Then there's a concatenated layers between the segmented image to the discriminator. Now, I can see what is going on at the bottom. That's the style gun.
Yeah.
But at the top, you say there's a concatenated layers between the segmented input to that of the discriminator. What does that do here again? The top path.
I'm a little confused about which part are you asking? So this part?
Right, exactly. Yeah, that path.
This part, the design of the DM, the design is used to enforce the alignment of the reconstruction and the segmentation map, so that we can make the to learn the joint distribution of the reconstruction and the labeled and the segmentation map. And the supervised loss is calculated. It's calculated on the labeled data. It's calculated on the labeled data. For the unlabeled data, we just calculate this branch. And I mean this part, the first function.
Yeah, I understand what you're saying, but once again, at the top branch,
yeah,
between the segmented image to
yeah.
The discriminator DM, you have some sort of concatenation of layers, right?
Yeah.
What does that do to DM? What is it that's actually taking place here?
In the original GAN, we use the discriminator to distinguish between the real and fake image. And here, the DM is designed to distinguish between the image label pair. We can input the reconstruction and segmentation pair to the discriminator. This is the first input for the DM. And the second input for the DM is the real image concatenated with its segmentation map this is the second input, and we want to do the discrimination between the image label pair, not just the image, so that we want to learn the joint distribution.
Okay, there's still a little bit of a gray, but maybe I'm just holding the time. So okay, let's just let's just continue. Thank you.
Thank you. The second step of the training is updating the encoder. And when we optimize the encoder, we freeze the G and discriminator. We can see that we use the two loss terms to update the encoder. The first one is LS and the second is LU. LS means the supervised loss on the labeled data. And the first term is the cross entropy loss defined on the pixel-wise label data. And the second term is the DSCE loss. About the loss and supervised, it is composed of the two parts. The first one is learned perceptual image patch similarity distance. It measures L2 distance in the feature space of an ImageNet pre-trained VGG19 network. And the second part is the reconstruction loss. And it is the L2 loss, similar with the original gain. Now let's come to the inference and the test period. We can see that when in the test process, we input a target image and we want to get the pixel-wise label Y for the input image. And we already know that in StyleGAN v2, we should do a generator inversion. So we should first get the W for the input X. We first map the image X to W using the encoder E, and then solve the inversion object. And we can see that we get the W by minimize this function. And the first term is try to optimize for reconstruction quality of the given image. And the second term try to regularize the optimization trajectory to stay in the training domain, where the encoder was training to approximately invert the generator. We do the gradient descent, and we will find the W, which makes this function minimize, and we can get the W to reconstruct the given image in a good quality. So after obtaining the W, we will pass it back to the generator to get the X and Y. And since W was optimized to minimize the reconstruction error between the X inverse and the X, it is realized by this function. And so we have this relationship. And furthermore, as the generator was trained to align, synthesize the segmentation label and the image, so we can expect the generated Y will to be a correct label of the reconstructed image X. So the generated segmentation mask Y is the almost optimal segmentation of the target image. After knowing about the
if you go back,
yeah,
still somewhat lost here. So W here, W plus. Are you talking about the training parameters, weights on the encoders?
It's represent the embedding. This part.
Oh, embedding. Okay.
Yeah.
Embedding. Okay.
Embedding.
I see. Okay. And so you are checking W plus. W plus is from the real image, right? X.
Yeah, exactly.
And then you're trying to compare that with the embedding coming out of the generator, right? The second term, E sub G sub W plus.
Yeah.
So you're really going a sort of a cycle here then. It's sort of like a cycle here,
Yeah,
going
yeah.
from generator back to the encoding.
Yeah.
So that when you go through the complete one cycle, it comes back consistency here, right?
Yeah,
For the
yeah.
scale. And so that's just simply saying, whatever the embedding space, I put it into the generator and then the encoder, it should come back the same. So
Yeah.
you're applying the two inversions here. And then X star is X star, okay, so that's the target image, but what do you mean by target image here? Because this is a style GAN, so is there a target image you can actually have?
Actually, I think the X star represents the test image.
Test image.
Yeah.
Yeah, I mean, that's what I'm wondering, because for style GAN, is there an input target pair?
Because this is a semantic segmentation task, so when test, we will have one image, and we want to get the segmentation map of this input image. So this is different. The proposal is different with the style GAN to some degree.
Okay, if they are talking about the encoder here, and if it is a style GAN, even through the generator, what you want is the semantic map should come out the same, right?
Yeah.
I'm wondering why that's not checked here.
I didn't
wait a minute.
you.
Oh, wait a minute. No, I'm sorry.
Yeah.
Wait a minute. That's yeah, that's done by the second term. That's basically what it is. The second loss is doing that.
Yeah.
The first loss, I'm not quite sure because I'm sort of uncertain about what this X star represents. Here it says down below, we have X inverse is estimated to be X star. But the inverse of what? The generator? Is that what it is? Or the inverse style transfer?
X inverse, I think it represents the reconstruction result.
Okay, so reverse of the style transfer, I assume, right?
Yeah.
Okay. All right. I'm not so sure how style can have a ground truth input and target pair, but this seems to be saying just that, right? X star is really a target style transferred image of X.
Yeah, yeah.
Okay. All right. Thank you.
Thank you. So let's come to the experiment part. And the author tests the proposed method in with three tasks. First one is the chest X-ray segmentation. The third is skin lesion segmentation. The third is face part segmentation. And it uses the dataset, including a small labeled dataset and a relatively large unlabeled dataset. The competitive methods include the three state-of-the-art semi-supervised method. The first one is mean teacher model with transformation consistency. The second is based on the adversarial training. And the third is guided collaborative training. And the author also compared with the variants of itself. It is represented by the hours node. It represents infer and image embedding using the encoder only, and doesn't do the inversion optimization. And for the first task is chest X-ray segmentation. The training set is CXR14. It is labeled and JSRT. It is unlabeled data. The test set include the test set of JSRT and the other 3 medical dataset. These datasets vary in terms of sensor quality and patient process. About the metrics, it uses the DSAE to measure the performance. And we can see that in the table 1, here is the quantitative results. In the figure, the trained labels represents the number of annotated examples used during training. And we can see that here are the results. The proposal has achieved a large performance improvement by the supervised method and the semi-supervised method. And from the quality results, we can see that the proposal, when tested on the out of domain datasets which didn't get involved into the training, it also achieved comparatively good performance. This column. And for the skin lesion segmentation.
So on this hours dash no, what does that mean? On the table, hours dash no.
Yeah. Here is the explanation.
Oh.
Yeah. We infer an image embedding using the encoder only, and we don't do this part. The inversion optimization, we just put the image to the encoder and take the output, send it to the generator. We don't do the inverse gradient descent optimization.
Okay, so that step's skipped. Okay.
Yeah.
Another interesting thing here is that for the case with 35 labeled samples versus 175, 35 labeled data samples seems to have better performance, right?
Could you please tell me which part? This part?
175 labeled, that one, you know. So on the NLM 0.9509, right? 0.9509 is NLM number for hours.
Yeah.
For 35 labeled, the performance is 0.9606. So it's doing better than 175 labeled data. So in other words, it's using less number of labeled data and still does better, which is interesting. Which means that it's used. How many unlabeled samples were used? How many in this case?
You mean the labeled sample?
Right? No, unlabeled. This is semi-supervised, right? So you use unlabeled.
Unlabeled data set is about 100,000.
Oh yeah, much more, right? And definitely. So it's learning more from the unlabeled data than the labeled ones here, it seems.
Yeah.
That's what it, at least in this case, it shows, right?
Yeah.
I'm wondering if they discussed this, because this is sort of an interesting trend here. So after a certain point, maybe label data is not providing as much value compared to really a large number of unlabeled data, right?
Yeah.
Okay, thank you.
Thank you. For the second task is the skin lesion segmentation. The experiment setup is similar with the chest segmentation, and the dataset for the training is ISIC, and there are 13,000 unlabeled dataset, and the test set comes from the test set of ISIC and the other 3 medical dataset. they also vary in terms of sensor quality and patient poses. And the matrix, the author takes the GC index as the matrix to measure the performance. And here is the example. The author used 40, 200, and 2000 labels respectively to train the model and get the performance when testing on these four data sets. And we can see that the proposal also achieve a good generalization ability on the out-of-domain data sets. For the third task is the face part segmentation. The training set is this one, and it offers the labeled and unlabeled data for training. And the test set comes from the test set of this CLEBA and the mat faces. The matrix, the author takes the MIOU as the matrix, and we can see that it also uses different number of label data to train the model, and the proposal also achieve a good performance. And here is the qualitative result of the proposal and the other methods. And in the below, here is an example when testing the proposal on the extremely out-of-domain data set. For example, here there are cartoons, and even in an animal face, the cat, the dog, and the horse, it can achieve the segmentation to some degree. And for this, there are staff, but with the similar appearance with the man face, and it can also achieve some achieve the semantic segmentation to some degree. Here is an example of the extreme out-of-domain segmentation. And for the ablation study, the author also trained a model with the generated data. As introduced before, we know that the proposal can achieve the reconstruction of the image, and it can also generate the segmentation map of the reconstruction. So we can get lots of synthetic data. So the author used the model to generate a large amount of synthetic but annotated image. And this can be used to train a regular segmentation network in a fully supervised manner. And it tests the performance on the face segmentation task. We can see that the method, the first one is deep lab real. It is represents the supervised training of deep lab V2 using 140 labeled real images. And this for the SIM, hours SIM represent training the deep lab V2 using only 20,000 synthetic data set. And hours mix represent training the deep lab V2 using both the synthetic and labeled real images. And the DIV represents the sample strategy. It's sampling without applying the traction trick sampling strategy, which results in more diversity but less visually appealing images. And this one represents applying this sampling strategy with a factor of 0.7. And
so can you explain these two strategies? What do you mean by truncation trick?
I'm not very clear about the detailed strategy.
Okay. this, I think, would be sort of an important part to consider.
Yeah.
What I'm wondering is this, because for this semi-supervised learning methodology, I'm wondering if the authors ever really mentioned about utilizing all the unlabeled data or some of it, right?
Yeah.
Because unless your segmentation comes out very accurately, if it comes out with some errors, it's going to be detrimental to the training. Your segmentation learning is going to be done with incorrect labels, right?
Yeah.
Basically.
Yeah, exactly.
So there has to be some ways of at least putting some sort of a threshold saying, with this segmentation, there's a certain level of confidence, and maybe below certain confidence, I'm not going to use it as part of the training, right? Have they ever done anything like that? Or is that what they mean by truncation trick here?
Yeah. That's the problem, very important. But the author didn't mention.
They didn't mention anything about that?
Didn't mention the detailed information about the strategy. It's just an application study. So maybe I can introduce the next seminar.
Okay, maybe that's something that you may want to maybe do a little bit of research, because that can provide some new methods, right? Because if you can find some ways of levels of confidence, and if you go back, earlier slides, when you computed the losses during the training, right? Some of these losses, you can use that maybe as an indicator saying this segmented image for the unlabeled data is inaccurate, so I'm not going to use it.
Yeah,
right?
yeah.
And maybe you can do it in a way like a curriculum-based learning. So in the very beginning, out of the 20,000 unlabeled images, maybe a couple of hundred comes out with the low levels of loss, and you will put that as part of the pseudo-labeled images for training. And then you keep on increasing that number as the segmentation gets better along the way. Maybe that's one way of improving this method.
Yeah.
Okay. All right. Thank you.
Thank you. And we can see from the results that by using the labeled dataset and make use of the large amounts of unlabeled dataset, the proposal can achieve the best result compared with other using different strategy or just train the model with the labeled data in a supervised manner, or training the model with both synthetic data and the real data. The proposal can achieve a good generalization for the out of domain dataset, the metaphysics. And finally, we land on the conclusion. In this paper, the proposal, the author proposed a fully generative approach to semantic segmentation. It is designed based on the style GAN v2, and it allows for semi-supervised training so that to achieve the strong generalization capability. And the author validate the proposal in the medical and the face segmentation. We can find from the results that the proposed method can generalize to paintings, sculptures, and cartoons. And it produces plausible segmentations even on extreme out-of-domain examples. For example, the animal faces and the staff with the appearance similar with the man face. And this can be attributed to the model's remarkable generalization. It is because it is designed with a style GAN v2 model and can achieve such a good performance. So that's the end of my presentation. Thank you. So is there any questions?
Can we go back to slide 8?
Yeah.
Okay, so now I understand the path or the two branches that's being shown on that picture. At the top, there's a concatenation part, which concatenates the face image and that of the segmented image together as an input. And then
Yeah.
it goes through the, and then it reaches to the discriminator. I think that's what that is. So
Yeah.
there is a path from the face image as well as the segmented image to the concatenation part. Okay, so that I understand. Now, coming back to the semi-supervised process. So how does the semi-supervised part gets into the picture? Here, it looks like it's all supervised training process, even though you have two different branches, one for the face and one for the segmented image. So my question is, how does this out of domain part get into the picture?
We can see from the overview of the proposed method, we train the model using the labeled data and unlabeled data. For the unlabeled data, we just calculate the adversarial loss and we don't and the image reconstruction loss. These two loss not relies on the annotation of the image. But for the labeled data, except these two adversarial and image reconstruction loss, we also calculate the supervised loss on the segmentation map. So we can say that this is a semi-supervised model because here there are some unlabeled data get involved into the training process.
Okay. All right. I think I missed when you said unlabeled. Could you just repeat that again?
Unlabeled, I mean
unlabeled, right? Unlabeled.
Unlabeled.
Right. How does when or how or when does the unlabeled data gets into the picture?
Okay. For the unlabeled data, we can use this figure to explain it. For example, here is an unlabeled data. We put it into the encoder and the generator, and we can get the reconstruction. And we calculate the adversarial loss and the reconstruction loss. When calculating these two loss, we don't use the segmentation map of this image. Unlabeled means we don't have the pixel level segmentation annotation of the input image.
Wait a minute. Why can't they use segmented as well as generated image pair for the DM loss, even for the unlabeled image? Because only thing that you cannot compute is the supervised loss, right?
We can see that this function, the DM, the loss for the DM is just calculated on the labeled dataset. DL represents the labeled dataset. We can see.
But you can still compute loss of DM even for unlabeled image, right?
We can't because we don't have the real annotations for the unlabeled image.
No, but that comes from you compute LS for that supervised loss, right? LS is computed using the label.
Yeah.
But L sub DM doesn't require the label.
Yeah, exactly.
So you can still use both of those losses, even for unlabeled images, right? I thought that's how this was done.
Yeah.
Because unless you do this, what this does is that it forces the generator to generate both style transfer as well as segmentation map that's consistent, right? That's what these losses are really going to compute and train it.
I'm also curious about this, and I'm waiting for the author to release the code so we can go deep into it.
Okay, yeah, I think that would be great if you can really, try the code, and because there's some avenue that you may be able to do some additional research and improve, and perhaps can come up with a better results.
Yeah.
Okay, yeah, so if this can be done on semi-supervised way with the arrangement, and I think with the code that you can get access to, I think that will be wonderful.
Yeah,
okay.
I will try later. Yeah.
Good, thank you.
So
thank you.
What I was telling you was that to judge the quality of the labels from unlabeled data, right? You can judge the quality coming from by looking at the L sub D M here.
Yeah.
I think.
Yeah.
If it is consistent, you say chances are that it labeled correctly, right? If it is not consistent, there may be some, errors in the way.
Yeah, maybe we can use some PSNR, such kind of metrics to test the performance, the quality. Yeah.
Okay. I'm still kind of uncertain why they even go through the style transfer of this. The objective is segmentation, semantic segmentation, not so much about generating another style here, right? That's not the objective.
Yeah.
So what does that do to improve the segmentation by putting in a style transfer here?
In my opinion,
maybe it's really that L sub DM is what really brings the value by generating some other image, but then segmentation image. Still, the segmentation or the that semantic segmentation has to stay consistent and remain the same, both on the style transfer as well as the original image.
Yeah.
Maybe that's what it does. Okay. Anyway, great. I really enjoyed the paper here and the presentation.
Thank you.
Thank you.
Good job. Thank you.
Thank you.